In this lecture, we're going to step through an example of application of the one sample t-test. But before we do that, we're going to take a little bit of a historical examination of the t-test itself. And so one of the big problems in statistical analysis is most often we don't know population parameter values. They're very often unknown, particularly the standard deviation. And so William Gossett was a undergraduate student majoring in chemistry and mathematics, and soon after graduation in Ireland, worked for the Guinness Brewery right away in the area of quality control and was in the process of examining different varieties of barley in order to produce better tasting beer. But one of the problems that Mr. Gossett encountered was that he had only very small samples to work with, and the statistics of the day were all based on much larger samples that were very close approximations to populations. And so this posed a problem in terms of trying to relate very small samples, which have very different types of statistical distributions, back to the population. And so during his work with the Guinness Brewery, Mr. Gossett basically developed new mathematics and developed what's called a family of t distributions that were similar to the normal distribution, but took into account the smaller sample sizes. And in publishing his work, he was not allowed to use his name as he was working for Guinness at the time. So he published it under a pen name or a pseudonym, and just the title of the paper was published by Student. And so to this day, the t-test is often referred to as the student t-test. But we're going to take a look at the application of what's called the one sample t-test in this example research study. And so in this study, the target population were young adult male and females that were physically active. So in the sample were composed of 15 healthy males, 15 healthy females, who were all volunteers. So of course, random sampling could not have been done. And so the objective of this study was to match a person's physical actions of, in this, as you can see in this photograph, a person lifting weights using a standard knee extension device, to what they perceived as the level of effort to lift that weight. And that was measured with this scale here. So here we see a scale that has both numerical and verbal descriptors, where a perceived level of exertion of 0 represented no muscle contraction. A value of 1 represented the person's perception that their muscle was contracting very light. Number 5 was intense. Number 7, very intense, so on and so forth, and would rate a 10 as a maximum level of effort that they were exerting when lifting various types of weights or varying levels of weights. And so the procedures here first involved examining a person's maximum strength generating capability in what's called 1RM testing. So the person was evaluated for how much weight they could lift with this exercise, doing one leg extension, only one time. They were only able to achieve one repetition of this particular exercise, which was knee extension. The experiment then had all the volunteers to perform 2 repeated repetitions with different loads, and the loads ranged from 20 up to 90% of the 1RM or the maximum weight, all presented in a random order. And so the outcome variable was the person's subjective rating of their perceived exertion or their effort after the second repetition at each of these loads by reporting a number on the scale. And so in this case, the research question was, does perceived exertion, which is a subjective measure out of 10, correspond to the percent of the weight lifted? So if a person was lifting a load that was 20% of their maximum load, so a very light load, would they rate that as a 2 out of 10 that corresponds from a ratio perspective of a 20%? How about a 5 for a 50% 1 RM load? So how would we go through the statistical process of investigating that research question? Well, we follow the exact same steps. We state the null hypothesis, the alternative, we choose an alpha level, whether it's 1 or 2-tailed. We state the rejection and retain rule. We compute the appropriate statistic. And then after the appropriate statistic is calculated, and in this case it will be a t-statistic, we then match that to the to step 4, the rejection retain rule. We make that decision, and then we write the conclusion in the context of the study. And so if we start with the null hypothesis and the alternative hypothesis, the null hypothesis is always going to be stated the same way, and we're going to investigate in this particular question the 20% weightlifting load. And the 2 represents the perceived scale value provided by the volunteers. So the null hypothesis in this case states that the sample measurement at a 20% weightlifting load would be equal to the population value of a 2 out of 10. Stated in a different manner, that the difference between the population and the observed value would be a 0. So in stating the null hypothesis, either one of 2 of these approaches can be used. We then automatically state the alternative, in that the alternative states that the sample will not be different than 2 at a 20% lifting load. Stated in a different way, we transpose the 2 to the other side, and that the difference would not be equal to 0. Moving on to the third step, we choose our alpha level. And because the consequences of a type 1 error in this case is not considered to be very catastrophic, we would just go with the 5%, the standard 5%. And because we don't know of whether the participants would rate a value greater than 2 or less than 2, we would just go with the non-directional approach and a 2-tailed level for the alpha, or for the type 1 error rate. We then state the rejection and the retain rule. And now this is a little bit different than the z-test. When we use a normal distribution, we now have to use a t-distribution that reflects sample size. So we use the t-table. We then find the degrees of freedom by using the equation of n minus 1. And in this case, the capital letter N refers to the entire sample size. So we're grouping all the males and females together. Because we had 15 males, 15 females, we have a total sample size of 30. We subtract 1, and we have a degrees of freedom of 29. So step 4 means that we have to find the critical t-value for a degrees of freedom of 29. So we go to the t-table, and I just clipped and just the relevant parts of the t-table for our usage here. But just to compare the one-tailed approach versus the two-tailed approach, if we select a one-tailed approach, our critical t-value is the value that separates 95%, which is everything on the negative side, in the negative direction of the critical t-value, and we're looking for a calculation of our final calculation that would place it in the 5% region. This is different than the two-tailed approach, where we don't know if the response provided by the participants are going to be greater than the test value or less than the test value. So we keep an open mind to that possibility, and we spread the 5% to the lower tail and to the upper tail. And so this represents 2.5% of all the participants that represent the population, 2.5% of the entire population represented by the sample. And 95% is captured between the negative t and the positive t. In going to the critical t-values, we'll take a look at the one-tailed degrees of freedom and the critical value. So at a 0.05, that's if we go with the one-tailed approach. We look up the degrees of freedom, we calculated a 29, and we see that we have a critical value of 1.699. If we select the two-tailed approach as we do in this problem, we have the same degrees of freedom, that doesn't change, but what changes is the alpha 2. So with the two-tailed approach, we use the alpha 2 row here, and we go down and we see we have a larger critical t-value. So the advantage of the two-tailed approach is we keep open the possibility that the final result could be greater or less than, but in doing so, it raises the value of the critical t, so it elevates the standard to which we can state that the results are statistically significant. And because we've already decided we're taking the two-tailed approach, our critical t-value is going to be 2.045. So the next step is to state the rejection and the retain rule. And so the rule states that we're going to reject the null hypothesis if the absolute value of our calculated t, so that's t with x of the average, x bar, is going to be greater than the critical t-value of 2.045. If it's not greater than, in fact, if it is less than or could be greater than or equal to reject, we retain if it's less than the critical t-value of 2.045. We then compute the appropriate statistic, but before we compute the appropriate statistic, what we have to do is actually collect the data from the research participants. And so because we predetermined we were going to test 30 people, we go through the process of going through steps 1 to 4, and then we collect the data, and the table on the bottom here are the results generated from the study of the 30 participants. And so our example here, we're going to zero in on the very light load that the participants lifted, 20% of their maximum strength. So at 20% of their maximum lifting strength, did they rate a value of 2? And so the average rating turned out to be a 1.21 with a standard deviation of 0.56. And so just by looking at this number here, we see that this number is less than the expected value of 2. However, we need to test this statistically. So we're going to use our equation in calculating the t-value. This is the calculated t-value, not the critical t-value. And so we have our group average, and the average here is specific to one situation. That situation is a light lifting load at 20%, and the average is 1.21. The population average to which we're going to compare that to is what we expect it to be at a test value of 2. And the S of X bar is the standard error of the mean of the sample. Remember, we do not have the standard deviation of the population. And so moving forward here, this is just repeating the previous slide. And so this would be a good time to pause the video, go through the calculation, remembering the first step is to calculate the standard error of the mean, and then from that point, calculate your t statistic using this equation. Okay, so presumably you're restarting the video and you've gone through this practice. And so we calculate the standard error of the mean, which is equal to the standard deviation, and this was already computed from the descriptive statistics stage, and we divide it by the square root of the sample size. Note here in this step, we don't divide it by the square root of n minus 1. That was already factored into the calculation of the standard deviation. So we just divide it by the square root of the sample size. And so we have our standard deviation, which was one of the first things that was calculated at 0.56. We have a sample size of 30. And so we end up with a standard error of the mean of 0.102. We then substitute all the values in the t equation. So we have an average of 1.21. We subtract it from 2.0 and divide it by 0.102. And we have a final t value of negative 7.75. And so a negative 7.75 puts it on the left-hand side of the t distribution, remembering it is symmetrical, but it's more platykurtic than a normal distribution. So 7.75 is a large number on the negative side. So we move on to testing that value against step 4. And since our calculated value, or at least the absolute value of negative 7.75 is greater than the critical t-value that was determined from the table of 2.045, we therefore reject the null hypothesis. And in rejecting the null hypothesis that the sample would be equal to the population average, which we assume to be a 2, we accept the alternative that it is not equal to the value of 2. And so we then write the conclusion in the context of the study. So in this sense, we state that the ratings of perceived exertion of our sample were significantly different. We say different because we had a non-directional test standard. So we say it was significantly different than the expected value of 2 in healthy young adults when lifting a load equivalent to 20% 1RM. But that still leaves open the question of directionality. And so can we imply direction? Absolutely. So we would state that in terms of the direction, which direction were the ratings different? We already know that they're different, and so we would just examine the average value of 1.21. It looks like it's less than 2.0, but the statistical testing gave us confirmation that it is statistically less than 2.0. So what we would conclude is that healthy young adults rate these values less than the expected value on the scale of 2.0. So this ends this part of our t-testing unit.